I will begin. Dear Father, we thank you for this day. Again, Lord, I thank you for the students. Just pray you to help us use this time wisely just to wrap up any questions that remain before the test. And again, Lord, I just pray that you'd encourage the students to just continue working and just do their best for your glory, Lord, in this final time, Lord. In your name I pray. Amen. Let's see here. So is the course evaluation links up yet?
Yes.
Okay, so if you would kindly wait to, when do we have till to do those?
Reading day usually.
Reading day, yeah. So if you kindly just hold off on that, I have a speech I like to give to try to color your responses. I mean, no, just so that we understand the questions more deeply. And I heard a rumor there would be cookies. So I didn't get that together today because, well, the sky is falling today. But come on. But that is upcoming. So Sam, are you giving the talk? Was it Friday? Friday. Okay. So before Sam's talk, I will give a brief talk about course evaluations. I will give you my handwritten ones, which you will fill out in class, and then somebody here will take them to the secretary. I will leave the room for 5 minutes for you to finish those, and then Sam will give his talk for how many minutes? Is it a 30? Let's aim for 30 minutes, because I think all that nonsense with course evaluations will take 20 minutes, provided I don't make too much of a show with the cookies. Although I do sometimes make a show of it. I don't know. Oh, come on. Seriously? I thought I had the right source. HDMI. Yeah? Come on. You can do it. All right. There we go. So anyway, there's that. I'm also working on when, I think the final exam for this course is pretty fixed. I mean, there's not really a question, but for some of my other courses, there's really an ambiguity about when it shall happen. So you can expect some sort of final exam announcement in the next day or two. I'm still trying to figure that out. That doesn't really matter to you guys, I don't think, because your exam time is pretty set. Now, if you have some sort of other time obligation for some reason, then you need to work around it, just let me know, and I'll see what I can do. But I'd prefer that everyone takes the final exam in here at the scheduled time, unless there's a really, really good reason to do otherwise. So this was mission 9, which I still have not posted the solution for, right? And we just glance through here. I've stolen some of Zach's and some of Sam's solutions for this one. Do I have permission? Okay, good. Just checking. Now, the first one, problem 81, this is a really neat argument. Here you actually get to use that homomorphism to the coefficient homomorphism, if you will. So if you prove that's a homomorphism, then you're able to see that the kernel of this map is exactly, I of x, and consequently, it's an ideal. Then to see it's a prime ideal, well, the first isomorphism theorem tells us that R of x mod the kernel of psi is isomorphic to the image, but it's a surjection, so the image is the whole polynomial ring with factoring coefficients, and well, R mod a prime ideal is an integral domain, and polynomials of an integral domain are an integral domain, so this quotient's an integral domain, so we have R of x mod this ideal is an integral domain, which then implies that I of x is prime. So I really like this problem. It's sort of an amalgam of 2 or 3 big theorems for us, right? And it's actually not that bad. There certainly have been much more insidious homework problems in missions 9 and 10, right? But if you tried to do this directly, like I did the first time I worked it gets really bad really quick, doesn't it? If you actually try to prove directly that that ideal is prime inside the polynomial ring of R, it's bad. You can look at my solution from last year. I think it was problem 110 or something like that where I did that. This problem's not too bad. Skip ahead here. So I'm just going to tell you. So I worked them out myself, although this solution looks suspiciously similar to Zach's. Not that you can see it. This one I wanted to talk about briefly, since I'd heard you guys say otherwise. I wanted to set the record straight. You do not have to calculate 27 things here. I mean, you can, but that would be the sort of most mechanical, silly way to do this problem. A smarter way would be to use an amalgam, like a combination of techniques. So if I'm looking for irreducible quadratics in Z3x, well, that's asking the question, can they be factored, right? Since it's a cubic, remember for quartics and cubics, they are irreducible. If they have a 0, we can factor them, right? I mean, so there's a theorem that if a quadratic or a cubic has no 0, then it's irreducible, right? So we can actually plug in values. Certainly it's quadratic, so I can check if it's irreducible there. But I don't really need to plug in values and do that, because if I can factor it, it's reducible, right? So like I don't need to plug in values into x squared to see it's reducible. It's not irreducible. It's irreducible. I mean, it's not irreducible. Now this one, if I plug in 0, 1, and 2, I get non-zero entries all around, so it's irreducible, right? It can't be factored. And fine, I had to plug in factors here too. But an important trick to notice about, like here, well, there's a common x. You've known this since the 7th grade, right? 8th grade, 9th grade, I don't know, some grade. You learned how to factor x out, right? And it's still true in Z3. Where am I? Yeah, Z3x. If it can be factored, it's not irreducible, right? This one, if you look at 1 plus 1 is 0. So that means that there's an x minus 1 that can be factored out. I didn't even actually find the factoring, but it suffices to, once I find 1, 0, okay, there's an x minus 1 as a factor, right? Now you could actually factor it. Wouldn't be a big deal, would it? What would be what was it, x squared plus x plus 1, right? So I got, what did I just say? I have x minus 1 is a factor. So let's say x plus 2 is a factor. And 1 is what? So I guess I got to put a x plus 2? Oh, okay. Right. So I guess my my point was that x minus 1 is also equal to x plus 2 in Z3x, right? So you can play these games. Factoring actually is very kind of fun in these contexts. Finally, the other one, and I can factor an x out. That one actually is irreducible if I add a 2 instead of 1, because all 3 values work out to non-zero. And then that's obviously factors x out. This is obviously x plus 1 squared, right? And then that one is also irreducible. So we have these 3 irreducibles. My point to you was, like I heard, you guys told me there's 27 things I had to do. But I guess you're saying if you did it the same way? Is this the one you're talking about?
The one we were talking about, I actually think, was on mission 10.
Oh.
That was the one about factoring over that.
Well, I feel silly now.
That extension field thing.
I feel silly now. Well, anyway, I still think that what I just said was worth saying, but maybe not for the reason I thought it was worth saying. X to the 5th plus x to the 4th plus 1. So you notice I plug in 0, I plug in 1. They're both non-zero, so it's irreducible. No, wrong, incorrect. Why? Right, there's fine print there. It's quadratic or cubic if you get a 0. If you don't get a 0 from all the values, then it's irreducible. But for a quartic or for a quintic, there's no such theorem. So all that was that do, but it doesn't give me partial information. What does it tell me? It tells me that there is no linear factor. Right? It tells me that there's neither x nor x plus 1. Those are your possible linear factors here over Z2x, right? Of course, you could already see that there was no x, right? And the fact that there's no x plus 1, I guess I could fiddle around with it to see it directly through algebraic manipulation for a while, but the theorem is nice. All right, what are the irreducible? So that means that we have to be looking for quadratic or cubic factors, right? And if you look at the degree, it's 5. right? So by process of, counting 5, it's what? It's 1 plus 1 plus 1 plus 1 plus, I lost track. Anyway, 5 ones, right? He sounds kind of German through a wall. I swear he just said 9. I have the sudden urge to pick up a chair and just throw it as hard as I can against the wall. But then telling the story of how I broke the board, it won't be fun. And it'll be fun. Is it worth it, though? These boards are kind of expensive. I don't know. Anyway, I was getting to a point. So if you think about it, since it doesn't have 1, it's got to be built from a 2 and a 3, right? Because we can't have a 3 and a 3. Because that would give us degree 6. We've got degree 5. So we have to be looking for a quadratic factor, right? So what are the quadratic factors over z2x? Well, they're x squared plus 1, x squared plus x, and x squared plus x plus 1. This is it. This is all the monic quadratics. Monic also, because that's a monic to start with, leading coefficient's 1. And so there's, that has to be monic, and the factorization also must be monic here.
Also, all the monics in z2x all the quadratics in z2x are monic.
That is also true, yes. It's inescapable. Could I have, no, minus is 1. Minus 1 is 1. Yeah, you're fine. I thought I found a way around it, but then I realized that minus 1 is equal to 1, so I'm dumb. But anyway, okay. Long story short, though, x squared plus 1. See, this is another nice trick. Look for difference of squares where it's not immediately apparent. This is it's an important kind of trick to look for. Anyway, x squared plus x plus 1 is the only irreducible. So that must be a factor. I mean, that has to be a factor. That's inescapable. But on the other hand, what does it factor out? I mean, what factors out? Well, you could do algebra. You could do long division. I chose to do long division to figure it out. Many of you probably just guessed it, and that's also fine, right? But here's long division. It shows you the remainder 0, which means that x to the 5th plus x to the 4th plus 1 is x squared plus x plus 1 times x cubed minus x plus 1, like that. And there's its factorization. Of course, you might worry that this could be reduced. Of course, we know that doesn't happen, because if it did, it would have a 0, right? And if this has a 0, then the original polynomial is 0. So this work is really not required. It's redundant, right? Logically, it's not necessary to prove that this q of x is irreducible. It has to be by what we've already done. But there it is. It's got values of 1 for 0 and 1. So it is, in fact, again, by that non-zero, if and only if irreducible, for quadratics and cubics theorem. Fun question. What else is irreducible in degree 3 in z2x? How many monic cubic polynomials are there over z2x? How many monic polynomials are there in Znx of degree k? I've got x to the n plus an minus 1, x to the n minus 1, a1x plus a0, where an minus 1, a1, and a0 are all taken from, let's say, z mod, what'd I say? K. So how many polynomials of that type are there? K to the n minus 1, right? Yeah, because we get k choices for this one, and then k, and then k, and then okay. See the pattern. So it's k to the n minus 1.
Or just k to the n.
What's that?
Yeah,
There's actually n, or k.
Oh, I'm sorry. You're right. It's just k to the n, because I can't count. Yeah, because we're going all the way to 0. You're right. Yeah. So, I mean, how many monic cubics are there in Z2X in principle? How many are there? There are 8, right? So if I ask you to find all irreducible cubics over Z2X, that's a reasonable question. And what's the reasonable method to solve it? Brute force calculation. Yeah, pretty much. So, you know, this is a problem in here is when to do brute force calculation, when not to, right? Because there's some problems where if you use brute force calculation, you're just up a creek, right? But on the other hand, if you try to do one that's brute force calculation with a theorem, well then that's equally bad. So how do you know what to do? I think time travel is the safest answer, but right? You should do your homework and, you know, try to understand concepts and stuff like that. But I think that the better answer, more pragmatic answer to you at the moment though is to try again, right? If first you don't succeed. So I like Sam's answer for 88. I would encourage you guys to study it. It's a good argument. Basically, what he does is he shows that he uses the division algorithm to pick on it, and he's able to show that yes, every element's either nilpotent or a unit, and he does it by dividing into cases. There's either the r equals 0 case, which forces nilpotence for the polynomial QP. On the other hand, if the remainder piece does have, if the remainder piece is non-zero, then it ends up forcing us to have the f is in fact a unit. So if you watch the help session for, what was it, last Thursday? What was it, Thursday? Was it?
What were we talking about?
This one? Well, you asked me if I could talk about this one, and I gave you, I gave an example of how this works out over r of x mod x squared. Yeah. And then we started from the basis of that example trying to calculate it directly, right? This is definitely a better way. So I was happy with this because, I mean, I tried to do a direct calculation in basically the analog of theorem 2, right? The theorem 2 from the quotient. Theorem 2 was problem 90. That, you know, if you take a polynomial ring mod a monic, you get a, let's abuse terminology a little bit, but essentially a vector space over the coefficient of the rings of the order of the polynomial. Be more specific here. That's not honest. It's not a vector space because the polynomials don't have to be a field. The coefficients don't have to be a field. Come on. Eventually. Where's the statement? Oh, here it is. This theorem. So if we have a commutative ring, you have a monic polynomial of degree m greater than or equal to 1, then the factor ring, r of x mod h, is given by that. So that's actually relevant to the problem 88 we're just looking at, right? Because it's a monic polynomial. So we know that in some sense that's what that ring looks like, right? And I knew that. And so like if you watch the Thursday help session from last week, I tried to use this way of looking at that object to prove directly that everything was nilpotent or a unit, right? And we made some progress on it, but we didn't get that far. Definitely the way Sam did it in problem 88 is better. So I would encourage you to look at that. It's actually not that hard if you do it the way you did it. So. On the other hand, I would encourage you to read Zach's arguments here for 90 because they're pretty good. I think he's got all the details. So Sam, you write solutions a lot like my brother used to write them. My brother had this gift of knowing exactly what professors wanted to see and giving them none of the details they didn't care about. It's a dangerous line to walk, right? Because if you have disparate worldviews than your professor, if you find different things interesting than he does, it'll get you into a lot of trouble really, really fast. And then, Zach, you write solutions more like I do, which is kind of carpet bombing.
I read everything.
Yeah. And they both have their use, you know? I think Zach's solution is probably more useful to you guys. Anyway, I'm sorry I ran out of time to write my own, but on the other hand, I'm not sorry because I think this is probably better than what I would have written, given that I have significant time pressure at the moment, and I'm not writing very good solutions, honestly. So I'm sorry about that. All right, enough about my failings. And strike that from the record before you fill out that pesky course evaluation, please. I should wrap the semester up like 2 weeks before the end. It's been the last 2 weeks just like talking about Disney World or something. I don't know. All right, I'll shut up. You guys have any questions? Yes.
Problem 97 of mission 10.
Oh, mission 10, yes.
And a particular subcase of that.
So I've not posted these yet, obviously, but I will hopefully today. Come on, where'd you go? Problem 97?
In the case that B is 0 and A is not 0, how do we...
Yeah, I didn't address that in this. So
Oh.
Sam had some interesting things to say about that. So
I didn't write that because I figured out the answer.
It's okay. We'll all be uninteresting together here. Let's see, 5.1, number 37. What, number what?
5.2.
Oh, 5.2, number 20. If A divides B and delta of A equals delta of B, then show that A and B are associates. Well, again, you guys, like I think I already told you by email, Sam, but you know, he tells us that the divisor function's only defined. Where does he define this pesky thing? Look at back on page 266. In general, if R is an integral domain, R has division algorithm if a map delta from R with 0 removed exists, called the divisor function, blah, blah, blah.
Sure, but on page 270,
Ah.
it says that an Euclidean domain is from R to N. So if that's a typo, life is good.
So he throws 0 in for Euclidean domains, but not for general integral domains, huh?
On page 266 for mine, it just says delta from R to N.
yeah, where's 0?
Oh, really? 0 is thrown out for mine. Hey. See, this kind of thing irks me. This is the 4th edition of this book. Wait a minute. Let me reserve judgment. Something going on? Something going on? Yeah, 4th edition. But what printing? But what printing? I am looking at... Where is the printing?
In the first page, it goes 10, 9, 8, 7, 6, 5.
10, 9, 8, 7, 6, 5.
That's where mine stops. Someone else has stopped at 2.
What happens?
Be up to 2.
Mine stops at 5.
Mine stops at 5.
Mine stops at 2.
2?
Yeah, there's a couple.
2? What we got?
He's got 1.
We got 2? We got 2, I got a 5. 4. So for the people who have printing, too, on page 266, you have that delta is a mapping from R to N.
Yeah.
This is very annoying. Let us suppose then that delta is defined from R to N then, okay? Since apparently he... So that problem then needs to also have it stated that, wait a minute, well, what's the trouble with 0?
So the thing is, even though delta is defined from R to N, it gives no properties that constrain delta to 0. So that's why you have to assume B is not equal to 0.
Well,
Just make any delta 0.
I think that causes issues with the sort of property of that thing where you have like delta of A times something is greater.
No, because it's assumed it's both non-zero.
Oh, yeah, so it excludes it there in the Euclidean definition. I don't know. It like, doesn't say anything about it.
Yes.
huh. Again, we're talking about problem 20 and 5.2. So what would the problem again be if delta?
If A divides B,
Uh-huh.
B is 0, but A is not 0, then B does not divide A. But if they're associates, it has to.
I'm sorry, say that again. If A, A is not equal to 0 and B is equal to 0.
It says in the definition here of the Euclidean domain that delta A equals 0 if and only if A equals 0. Right on the second line on 2
Oh, no, that's not the definition for Euclidean. That's
Or
specifically-
of the division function.
that's specifically for quadratic domains. Quadratic. It's just using estimation.
Oh,
Well, anyway, this much we can say for sure. 20 makes sense if we assume A and B are non-zero, right?
Or even if you just assume B is not.
Or just B is non-zero suffices. Okay. Well, I don't think there's anything particularly interesting to talk about there. It's just, I'm sorry. I'm as annoyed as you are, if that's any consolation. Oh, and this is more interesting, but not what was asked about. But let's see here. Other questions? Here, let me just, what's this test on? Test 2 was on what? Was on advanced group theory, quote unquote advanced group theory. The group theory which is more advanced in this course, right? Probably better description. So test 3 is on rings, right? So where do we start with? We started by talking about what's a ring, what's a general ring or an RNG, right? Talked about what subrings are, what they're not. We had some theorems about idempotence in rings and nilpotence in rings, right? Probably what's the most important theorem about a nilpotent element in a ring? I think that's fair. If I add a unit, if I add a nilpotent element to a unit, I get an invertible element. Yeah, assuming they commute. I think, but if we take 1 plus a nilpotent element, I think it's one commutes with everything. So very good. We talked about what's a domain versus what's an integral domain. What else did we do? We talked about the isomorphism theorem for rings, right? Which gives us, I mean, when I say isomorphism for a theorem for rings, I'm thinking about a couple different things at once. I'm thinking about the fact that the kernel of a ring homomorphism is an ideal, right? I'm also thinking about the result that the domain of the homomorphism, mod the kernel, is isomorphic to the image, right? Both of those things together I refer to collectively as the first isomorphism theorem for rings. Then we talked about why the structure of an ideal was necessary to define factor rings, right? And then what else did we do? We looked at properties of ideals, right? We talked about how you can add them. We talked about what a principal ideal was, right? We proved various properties of principal ideals. We worked on how to find elements of orders of elements in a ring, in a factor ring, right? You guys had a lot of trouble finding orders of elements in a factor group in the last test. There was a lot of uncertainty there. Maybe some of that's kind of abated by now, since we've been working with factor groups still, right? Because every factor ring is what? It's first a factor group, right? With respect to the abelian group structure there. Yeah. What's that? Additive. And it is kind of funny, right? Like, we're working with right cosets for the group stuff, but all of a sudden we're working with left cosets for the rings. It's kind of quirky, isn't it? But I'm not sure. Have any of you, in your reading and thinking, come to a understanding of why he did that?
I think it looks nicer.
It looks nicer.
Well, addition looks nicer with left cosets, but then it should be commutative, so there's not really a distinction there.
Addition should be nicer with.
Well, I mean, because addition is sort of by
Yeah,
convention.
I almost wonder if he did it just so you would see the distinction in the concepts. I don't know. Maybe just to, I'm not sure. I asked my brother. Maybe he can see a deeper reason. Yes, Kang. Speculate, please.
I mean, I learned some chapter theory, and it's the same quotient object thing. I mean, there's a universal construction for any structure like that, or a quotient.
I mean, you can either do it left or right, or
Yeah, in some sense.
right. I do think it's just a choice of notation, and it's not that interesting, but.
I mean, you can do any algebraic quotient things on any algebraic structure like vector space, algebra, and it is a universal construction.
Yeah. Let's see here. Then, so once we understood what the factor ring was and how to do some calculations in it, we started asking questions about what kind of ideals there were, right? And we started talking about different types of elements in a ring. We talked about associates. We talked about units. We talked about nilpotent elements, of course. And the interplay between these three different, characters. We introduced the notion of a prime inside a ring. Or integral domain, I guess. Where do we define prime? No, a prime element. Because at some point we have said things like,
We only define primes in UFDs.
in UFDs, unique factorization domains.
No, sorry, we define it in arbitrary integral domains.
Okay, that's what my thinking was, is we defined a prime in a commutative ring with no zero divisors, an integral domain.
Yeah, the deal was that we had a limit that if it's UFD, then there's a component. So that's what we.
But we had an example, right? We gave an example in z adjoins square root of, I think, -5, or maybe -3, I can't remember, of an element which was prime, but was not irreducible, right? Or the other way around? Which way was it? The other way around? It was irreducible, but not prime, right? And so what was the definition of prime, I guess, is my question, you guys.
Prime defines, or P divides AB implies P divides A.
That's Jonathan, was it? Yeah, that's the definition of prime element. What's the definition of prime ideal?
AB in the ideal, that implies either A is in the ideal or B is in the ideal.
Prime ideal said if A, B is in big P, that implies A is an element of big P, or B is an element of big P, right? And we had a homework problem which studied the interplay between these two ideas, right? Pretty sure. I remember writing the solution out to it recently. It was part D of problem 84, I think, in fact. This one here, right? So part D says show RP is a prime ideal if and only if P divides A implies that, right? Which is to say that the ideal generated by P is a prime ideal, right? If and only if what? P is prime, yeah. I say generated, but I probably should say it's the P multiples of R. Is that also? I'm trying to remember what. Yeah. All right. So we talked about prime ideals, right? What other kind of ideals did we talk about? We talked about maximal ideals, and was there another kind of ideal we talked about? What's that? Principal? Yeah. So it's important to know those definitions and some of the basic theorems. I think the basic theorems, for example, if we have a ring mod a prime ideal, what can we say about that? Ring mod prime ideal. The factor ring should be a integral domain. If we have a ring mod a maximal ideal, should be a field, right? I think we need to have commutative rings for both of those statements to be reasonable. well, let me restate that. They're certainly reasonable if R is a commutative ring. We have said a smittens of things about non-commutative rings early on, and I remember some of those things.
I think both of those theories you just stated were bijections, I believe.
But I think they're happening in the backdrop that R is a commutative ring. Yeah. But yes, those are if and only ifs. Those are if and only ifs for commutative rings for sure. How about what if we know that it's finite? What if we have a finite ring? And we have, a finite ring is an integral domain. What else can we say? It's a field. All right, very good, very good. Is that true in the infinite case?
No, that's true.
Certainly not. What's a good example of that? Integers, yeah. So those are the... Then, of course, there's the discussion of PID versus Euclidean domain versus UFD, right? What's the order of operations there, so to speak? What's that? Euclidean domain implies PID implies UFD. Can you prove that the polynomial ring form over a field forms a Euclidean domain? How would you do it? Can you prove that the integers form a Euclidean domain? How would you do it? Define delta as the degree of the absolute value function. Another useful theorem for us, because the right, I guess, well, the full proof, admittedly, that the proof that fx, I mean, to show fx is a Euclidean domain, what's that require us? I mean, what is... this, I don't think I actually did the details of that in class. It's in your book, right? He actually proves that the division algorithm, which is based on the degree function, right, is a division algorithm. So that's what's required to prove that polynomials form a Euclidean domain, is that there is a division algorithm. And, well, the degree function is what? It's the, I think it's the divisor function here, right? Yeah. So I guess maybe restate my question. I'm not sure I stated it correctly. Can you prove that fx is a principal ideal domain? That is something you ought to be able to do.
Other than just showing it's either the length domain and then showing that implies principal ideal.
Yes. So this is a good point. If I ask you to, right. Things, the more you know, the harder it is for me to test you sometimes. What kind of language should I use to get you to realize which kind of argument I'm looking for there?
Just say what you don't want us to use, and we'll do something else.
I should say something like, show from base principles that fx is given that, well, yeah, if I prove from base principles that fx is a PID, then the latter argument has the base principles in it, right? Then if you want to prove that fx is a PID by the chain of logic that Sam was outlining, then you'd be obligated to prove the division algorithm works for fx, as those are base principles. But this is much more horrible, right? Because to prove it's a PID, all you have to do is look at the argument we gave in class, which was look at the set S, which is the degree, the degree of f, such that f is in the ideal, right? Choose a non-zero ideal. Look at the set of degrees of those polynomials rather. And by well-ordering principle, there has to be smallest one. Then you can proceed by the division. Oh, you still need the division algorithm. Curses.
So you can assume the division algorithm
Yeah.
that if you're going the
So I need to be very careful with how I word that test question is what I'm getting at here. All right, I'll think of something. Obviously, there are two different lines of logic, right? There's a direct proof by, which by the way is the proof that a Euclidean domain is a principal ideal domain. That proof is the same as the argument I'm trying to get at here. It's the same stupid argument, right? But they are different. I guess one way I could, sometimes I'm interested in what Sam just said. I just want you to show me that you understand and recognize that the fact that a Euclidean domain is a principal ideal domain, didn't know that result, and to tell me back that result. So I guess the way I would get at that would be, give me one sentence which explains why fx is a PID. And their Sam's sentence would be good. fx is a PID because fx is a Euclidean domain with respect to the standard division algorithm, and hence a PID, as UFD implies PID. I think I just made 2 sentences. Sorry, I can't live my own instructions. Maybe 3, depending how you're counting. I use run-on sentences, though, so, I allow you to do the same. I will, if we have a doubt, if you have these kind of deliberations, you can always ask me during the test. I will try to give you a nudge in the right direction. All right. Or I might tell you can go either way. I don't know. Or I might tell you nothing. These are all possibilities. Most of you have done your homework, so you ought to be more or less ready. Right? No. He's head shaking. No. I think it should be clear to you that irreducibility is a good kind of test question, right? Because it's pretty computational. It's something you definitely, most likely the problems I can ask you would probably not have been able to solve before this class, setting aside King. And I'm talking about irreducibility, though. You are talking to me about irreducibility in calculus 2. Very annoying. Not all of us have studied, contest math. It's a kind of, right? I mean, but I certainly haven't. Anyway, irreducibility is a nice topic for test questions. The ones like I was doing at the start of class today, but the other, just irreducibility over Zx. What is your main, there are two kind of main tools to use there. What are they? Yeah, exactly. No roots for the quadratics and cubics. The other one would be the reduced mod to prime, right? So the reduction mod p theory was sometimes very nice. And then, of course, when it happens, it's wonderful, and it's the easiest thing. It requires almost no thinking. It's magical. It's wonderful. The Eisenstein criteria, right? So if you can use that, that's fantastic. And then there's another thing. We proved last time the rational roots theorem, right? So that is at times also useful because we have a theorem that relates irreducibility over Z to irreducibility over QX, right? That was something we had mentioned, but we may have forgotten about. So I would say refresh your mind, make sure you know all the irreducibility theorems that you can use, and that's just a lot there. We've also done a fair amount with adding ideals and intersecting ideals, right? So it wouldn't be surprising to see a question that was something about that stuff. As I mentioned before, you should know what associates are, right? Associate unit. We had a lot of nice theorems about that. Sadly, I did not cover the partial fractions section. I'm sorry about that. I really wanted to. And again, I hope some of you read it. If you read the argument, it really is nothing more than a straight application of what we've done. And the proof of partial fractions really follows from just unique factorization of polynomials. It's not that bad. if you're ever interested in studying when does partial fractions work in a more general context, my brother actually spent the better part of a semester with a good undergraduate, like working on that question, and he wrote a paper with that kid as a result of it that studies, the question of how general can you do partial fractions. And so, if you're interested in that, look up my brother's paper. I would tell you the title, but I forgot it. That paper. Well, anyway, if you email me, we'll figure it out when your interest occurs. Other very important theorem I've forgotten to say. What is probably the most important theorem about, so we've talked about polynomial rings, right? In modding by ideals. Mostly we've talked about modding by ideals generated by a single polynomial, right? You could also talk about polynomials generated by modding two polynomials, right? You might wonder what's the interplay between those, right? You could do that. I wonder what that would. Well, that was problem 89, wasn't it? Problem 89 was kind of about that. But, or was it 99? What I was getting to, though. So f of x mod p of x is a field when what?
P is irreducible.
P is irreducible, right? So the fact that irreducible polynomials lead to maximal ideals inside fx, that's pretty important, right? And I would hope you might have a shot at proving Kroneker's theorem if I was to ask you it. That actually wasn't that bad if you look at the proof we went over at the end of last class, right? I mean, I spent all of about 3 minutes on it. It almost made sense to you, maybe. If I spent 10, it would have been like, oh, this is really simple. So I would encourage you to look at the proof of Kroneker's theorem. That makes a pretty nice test question, actually. So anyway, that's all I think of at the moment. See you guys. And don't forget, no filling out course evaluations until Friday. You already did. How dare you? Wait a minute, who else in here has already filled out a course evaluation? No cookies for you. All right. See here. What's that? No, I can't see them this year. One year I could see them as they were being done. That was amazing.
That would seem advantageous. Finding out.
Helps me decide whether